you go. So my name is Chris Okut. I work for the Army Research Laboratory. Rob Randall, you heard his briefing yesterday. He's my boss. So we're out here in the rain and growing things. And I'm here to talk about the meteorological sensor array. And you saw some of it on a slide earlier. I did give you a little handout that's getting wet. It has kind of a picture of the overall domain. You can see the boundary of Jornada on here to see that we pretty much cover most of the range. We go out about, well, to basically the boundary of College Ranch that way, and then all the way up into the foothills of the San Andreas. And to orient yourself on here, it's getting real wet. The UAS runway arrow dropping down, that's Tower 1, that's this tower. So it's kind of right in the middle there. And you can see a dominant wind direction too. So we're super excited about this because the wind pretty much comes from right over there where it's nice and open. So we have this really clean fetch, minimal roughness, almost no topography there. And it comes in and then hits our towers and then goes and foothill and so on. So it's really a fantastic place for process studies. A little bit about our tower. On the map, you'll see green and blue. They're small, but they're green and blue. Green is 10 meter, blue is 30 meter towers. 30 meter tower, for example, is out there. There's one. So it's quite different. We very much prefer those, but they're a lot more expensive. So 10 meters is good too. All of the 10 meters are basically like this. This is a standard configuration, and then we add additional instruments to it. This one has a couple weird cameras on it. That's not standard. But the 2 meter level and 10 meter level is standard. And at each level we measure wind speed and temperature. The sonic anemometer on the left there, it measures, really it's all three components of velocity by sending pulses from one transducer to the next. And then based on time of flight and the speed of sound, it can back out the velocity. So it's fantastic in that there's no moving parts, nothing to really break, except the crows, they break those 10 pieces off. That's the way it goes. And it's 20 hertz data, so 20 samples a second. That's where we're after things like the fluxes, like shear stress, momentum flux, heat fluxes, what's coming off the ground, all of those types of things. Non-mean measurements. You can still get wind speed and direction out of it, so we can back out mean type measurements, mean quantities. We also have a temperature sensor at 2 meters, and then a temperature and humidity sensor up there at 10. Actually, it's opposite. This is a TRH, and that's the temperature up there. The sonics do give us temperature fluctuations, but it's a little different, and you have to be careful depending on how moist it is. With the sonic temperature, it's not exactly regular ambient temperature, but the fluctuations are good, so we can use the temperature fluctuation. All this data is collected. You can kind of work your way in. There's nothing on the ground to be worried about. Data comes in, and it gets collected by, there's a couple options. The slow sensors, so that's all like the 1 hertz stuff, that gets collected with a data logger, which has a serial connection to a computer in here. You never know what's going to be living in here. So here's our data logger. You can see some stuff's plugged in here. That's all the slow stuff, 1 hertz. So the temperature, TRH, temperature up top, rain gauge, it's still 1 hertz. Not that it changes every second, but and then that's fed into the computer. The sonics, which are 20 hertz, they feed in through serial to the computer, so we can take much more rapid data that way. And then everything is set up so it gets sent back to headquarters, where it's concentrated into a database. So we have on-site storage. There's a terabyte SSD drive there. If something goes wrong, we're always collecting locally, and then when the network's back online, it can send it to headquarters and back to main host, so through the network. If we go back to this wet handout, there's more information here below about the surface energy budget, and there's already a question about a LTER. So this tower is kind of a minimal configuration. Full surface energy budget would be shown here, and there's 3 sites that have those. One of them is the 30 meter tower in the middle. So that site, it has a lot more levels, because we're always interested in the profile near the surface of temperature and velocity, for example. we're going to get a linear profile. We have two sites, two levels. So some of them we added 4 and 7 so we can resolve that better. The tower in the middle, it has 6 or 8, I can't remember. It's been 3 or 4 years since we put it up. But, so I mean, you can much better resolve the details. In addition, it has a LTER. They're at the same level as a sonic anemometer. That's pictured right here. That's so we can get latent heat fluxes, so moisture-related properties.
It's 10 meters or just the one at 2?
It's at 8 meters, the sonic, or the LTER. Yeah, and it's at the same level as the net radiometer. So we're getting all components of radiation, shortwave, longwave coming in, what's going off, water vapor fluxes, CO2 fluxes. Then we get into the soil properties. So all this stuff down below, it's in the soil. You guys are ecologists, so Rob and I really like working with you guys, or the people that I know at least that are ecologists, because there's this really interesting connection. I mean, there you got the atmosphere and land interaction, and a lot of what drives the atmosphere happens in the soil. So we care about soil moisture, soil temperature. The little cables coming off over here, in fact, that's what we're measuring. So this is a pretty standard 5 and 10 centimeter soil depth. It gives you thermal conductivity, so how easily the water flows. You guys know this stuff better than me. And then we have heat flux plates. That's something we're after. They're buried down in the soil. Water content, arrays of thermocouples to get the gradient, the thermal gradient. Now if you go to the back, it's the rest of the information. And I mean, we've talked about tower-based stuff. I mean, it's awesome. It's persistent. This thing runs all the time. We don't really have to worry about it. They do go down, but then we come out and fix it. You know, something chewed on a cable or something. We fix that. No problem. Back in action. But it doesn't give us anything above 10 meters in this case. Or in that case, nothing above 30. And certainly there's things we care about above 10 and 30 meters. So that's when you get into either remote sensing on the back, like Doppler LiDARs, or aerial platforms. So we do use Doppler LiDARs out here. We can pull them into the network. They can operate remotely, either off a PV setup like this, or generator, PV preferred, certainly. And what that can give us is the velocity field. And it can go up to approximately the boundary layer, which here could be up to, say, 3 or so kilometers in the summertime. So it's pretty far up. Totally dependent on the aerosols, the moisture, what's happening. So we might only get, 800 meters in the vertical or something because of lack of aerosols. It's very clean in the desert. But it can give us this hemisphere of velocity. So that's key, because here we just have a point measurement. And really we want gradients. We want things changing. We want a volume of information. We don't want little points all over. Now, in addition to that, we have background measurements here at the bottom. So it's quite key. So a radioson is pictured there, and in the environmental state, really we have the background is driving the local processes. Some of this was in Rob's briefing yesterday. So we have to understand the background conditions to understand what's happening locally. So they call it synoptic scale, so large scale stuff. So radiosondes are the best way to get that. You can see a weather balloon launch there. It was from the runway over here, actually, during an acoustic study. And that can give you all the information: pressure, temperature, humidity, wind speed, direction, up to, say, how far up? Way up. Way up. Really, really, really far up. Farther than we technically care about. But we do need that information to know if it's like a regime that we're interested in. For example, we had a study where we were looking at synoptic interactions with the mountain. So then we needed all the days to be the same background conditions so we could compare one day to the next. Because otherwise you're going to get different processes. There's a balloon here that's tethered. It's on a winch, so we can do profiles with this balloon. It's called a tethered lifting system. You can put different instruments on it, pretty much anything that it can lift. And that's fantastic for smaller vertical profiles, say from the surface to 200 meters or so. It totally depends on what you're after, though. I mean, you spend so much time going up and down, so the higher you go, the longer time in between profiles. So it depends on what you're measuring. But that's a fantastic way to sit at a certain altitude. We could go up to 100 meters and sit with our balloon there and do temperature and velocity fluctuation measurements, for example, or whatever the instrument package happens to be. And then aerial platforms in terms of UAS certainly are of interest. We do have one fixed wing that's pictured here, but it's a little bit problematic. But we have a lot of interest in aerial measurements. I think a lot of you guys have interest in aerial measurements, the spatial part, right? I mean, you go from point to some spatial knowledge, and it's quite key because, at least in the app, I'm sure you have the same problem. It's very hard to figure out what's going on from a couple points of information. You know, what happened before it hit here? You need to know that too, for example. You need to know upwind, you know, is there a mountain there? Is there topography? What's the temperature, velocity profile? What are the conditions? You need all this information to know what's happening right here. So we have that issue quite frequently. So we have 62 towers now. This area is kind of the central core. If you look at the first map, that's probably quite wet by now, it has a ring. And there's 12 towers concentrated in a ring. It was originally designed for acoustics, but it's generally good for propagation. For example, right now, what's the environmental effect on the propagation of our data back to headquarters? I mean, certainly that changes throughout the day. It's affected by the surface heating. In fact, it's affected by the refractive index. Changes in that. You get ducting. It changes how it travels, how fast, the range, things like that. So there's a lot of different things we can do with this sort of configuration. This being part of the propagation array. The rest are kind of scattered about. Some are at kind of boundaries, so we have boundary condition information, what's coming into the domain. Some are more just kind of spaced out for model verification. Depending on how much you know about the domain, there's a lot of dunes up in that direction. There's a lot more shrubs, a little bit thicker that way. We get grasses over there sometimes. The foothill is quite different as well. So we kind of scattered about. And in the foothill, we have towers at a 500 meter spacing. So it's very dense, micro scale in nature. And the idea there is that, well, you can kind of see it. It's the foothill right over there. Just a little outline you can see. Base of the San Andreas. The idea there is, you know, can we simulate the flows due to the heterogeneities there? There's rocks, there's all these different land use, different materials. There's these crevasses, gullies. You can get really shallow gullies flows. Do we resolve that in our models? How well is our land surface parameterizations working? Things like that. So that's kind of the spiel of the MSA. Guys have any questions?
Are you doing balloons on a regular basis, or is that project specific?
Project specific, definitely.
So there's 62 of these 10-meter towers.
62 total towers. So we have, I guess right now there's 61 10 meter and then the 130.
Oh, okay.
Yeah.
Does the Transect continue in the Tularosa Basin, like on the east side of San Andreas?
We would like it to. I mean, ideally we'd go right up the San Andreas there, that nice 45-degree slope, and then back the other side down to the park. And that's in the plan. We ran into a lot of issues on the slope with the refuge.
Okay.
So we backed off on that. But we do have plans on the other side. It's just funding dependent.
Okay.
So how far do you get up? About halfway in elevation up the mountains?
Oh, Rope Springs is as far as we go. We can't go any farther than that. That's the refuge.
Oh, okay. So how far up the mountain is that?
Not far.
Okay.
Quarter at most.
Mm-hmm.
Well, you can kind of see the outline of the foothill. So they were not interested in our observations. So I think we just need to find the right people. Because what they're doing is not that different than our interests too. I mean, we want to understand the environment. They have their own concerns up there, the sheep, the refuge. You know, they have fire concerns. So it's not really, the data is useful for everything. We just happen to be defense and funding.
So have you done modeling verification studies yet? What was the initial kind of baseline that came out of that? Or is that
So really the most of what we've done so far was it was more on the synoptic stuff, and the model did really well. It ramped up maybe an hour or so late, but the wind direction was right on, and the magnitude was within 10% at most.
and that's like a wolf configuration? Or
Yeah, Wharf, like a 931 Wharf configuration. So it's, I mean, for synoptic cases, it's doing really well. We're moving on towards more stable boundary there, and the soil moisture too. Right now is what we're looking at. So I don't know that it's going to do so well in those cases.
Have you had a chance to look at any, like the near surface winds at all? Like the really low, up close to the ground?
I mean, we did look at the 2 and 10 meter, but nothing below 2.
Okay.
I mean, the Wharf, it's using Mononabucock below that anyways, so it's a little questionable, especially as you drift towards non-homogeneous areas. But at 10 meters, it did really well. So at least in the recent paper, we compared the 10 meter. The Z10 is pretty standard.
How long do you plan to operate the sensor array?
Indefinitely. I mean, ideally, we can get a climatological catalog of data. I mean, you can imagine, okay, you want to test, just an example, you want to test your modeling configuration. How well does your model do in arid environments when it rains? Well, there's only so many days it rains, so you have to have this persistent collection. So at some point, we'll have 100 days of rain, right? So then you could just go through and you pick off those 100 days. When there's snow on the ground, we'll have 5, but you know, so be it. But otherwise, you just can't do it. Like you know, a lot of our experiments are set up where we go somewhere like Portugal. We set up a huge experiment for a month, spend a ton of money, and then maybe we get conditions, maybe we don't. We had this study where there's this double ridge. We thought that a climatological study said the wind was going to come in perpendicular to the ridges beautifully. Yeah, that happened like 3 days. And then it's over, and then now you're looking at cross valley and other things that were not even necessarily on your interest. So it's it's the inverse problem. But that's also a problem too, because it's very open-ended and loose. So it's kind of hard to say what your impact is because it might not be realized for a lot of years. Yeah.
So what is the time lag between the measurements and like the processing? I mean, is it weeks
So
or
we are.
real time?
It varies. It varies is the answer. So some of the data is offloaded through something that's real time for a base set of towers for another project. The bulk of the data though is just being collected right now and just preserved. We have gone through a lot of issues with networking out here. Turns out networking 62 computers out here is not easy on PV power and with the internet. But now we have CenturyLink, 200 megabits upload download all the way to headquarters. So that's a game changer for us.
Oh, yes, thank you.
We're happy. There he is. Thank everybody. Great.
Are you retaining the 20 hertz data from every instrument?
Absolutely, yeah. I mean, all the stuff I care about personally is fluxes, so I need that 20 hertz. A 5-minute average does nothing for me. I don't have any interest. That's not true, but I mean, who doesn't want to just look at wind speed and direction, whatever. But when it comes to research, it has little interest to me.
Having all these 60 estimates of roughness length on its own could be really interesting.
Oh, totally. And then you have the seasonal
It's
changes
remote
too,
sensing,
and
yeah.
there's so much to do. But I think that's a problem we have. A big problem of ours is that we have so much to do, and then it's the question of like, what can we do now? And all these different time scales of interest and of potential and resources, and so that's why we really like teaming up with you guys. The more people, the better. And we've had great success working with Brandon so far and the crew, and we're happy. We just want to keep doing a lot more of it. We want to speed up the process. We want to solve the mysteries of the Jornada. At least the land-atmosphere interaction mysteries.
So what's the
Maybe
point
one.
of the camera?
The camera. So, okay. Well, the camera, what it's doing is it's keeping track of cars going by. Now, why would we want to do that? I mean, it's quite easy to detect a vehicle from a camera, right? Camera, I mean, you have vehicle, no vehicle. They do this all the time. Algorithms are not super good, but they'll still give you an answer. But the question is, what if you're somewhere and you don't have cameras and you want to detect vehicles? Well, you're going to ideally use any sensors you have. Whatever. You're just driving through, you have all these sensors. So there's thousands of sensors out here. Some of those will likely tell you if there's a vehicle passing by or not. But you got to figure it out. So in that case, the idea is vehicles pass by, we pick them up on the camera, and then with the 2 meter and 10 meter sonic, we look for fluctuations and then try and couple it. So we try and teach the algorithm whether there's actually a car there or not. So use it as truth. Right?
Are you getting a signal?
Yeah, it works really well. But I fear that it's only, well, I think it can only work though if the wind's blowing this direction. I mean, there's stats. They did a test and it shows like 97% when you use both levels detection.
Wow.
And it was just like, you know, they were super excited, and I'm like, well, what if the wind's blowing that way? I mean, it can't work, right? But I don't know. Quiescent periods, maybe. I mean, there's weird stuff going on. It'd be the larger signature. But at least if the wind's blowing this direction, with one sonic it's like 93%, with both of them 98% accurate. And then they can even start to look at, oh, is it like one vehicle or is it several, is it a big truck, things like that. So it's just thought of how do you use environmental sensors for other uses, really. How do you pay for that CenturyLink internet?
Do you have any air quality sensors up on any of the towers right now? Do you have like methylometers or particle counters? Or?
No, we do not. We do have Nick at his main soil erosion site out there. We gave him a couple of those PSI dust racks, so he gets and they're separated vertically, so he can get the fluxes from those. We provided those instruments, and nothing in addition.
How about, did you have visibility? I can't remember if you said that or not.
No, we do not.
We should write a grant.
We should. We should.
We're hoping you get us money soon.
Yeah.
Yeah, we're counting on you.